Okay, just one last thing I wanted to talk about here, just to give you one more example. This is file number 48 on the website. This is one more example of the Model 98. Or actually, I think we use Model 99 here, doesn't it? So this was slags, molten oxides containing sulfides. So you have two kinds of anions, oxygen and sulfur. And so you can use, you have the two sublattices, oxygen and sulfur on one sublattice and the metals on the other sublattices. On the other sublattice, so here we use the Model 98. This was Yunbei Kang's postdoc work here. And so we looked at all the data for sulfur dissolved in slags as sulfide, that is S2- ions. So this is under relatively reducing conditions. If you have your sulfur, if you have your slag and your sulfur and you're under oxidizing conditions, then it dissolves as sulfate. If you put it under reducing conditions, it dissolves as sulfide. Okay, so dissolving it as sulfide. Again, then, where this is, we're using the, so here you have your system: silica, calcium sulfide, silicon sulfide, and so liquid slag. So here you have your quadruplets Si2O2, here your quadruplets are Ca2O2, CaS, and you have your binary quadruplets and your reciprocal quadruplet. And you can look at this as an example of the whole thing, and he applied this using just about all the sulfide data. Sulfide capacity data really means sulfide solubility. So we have sulfide, these are sulfide solubilities in different slags. This is your, basically your silica calcium slag, and this is your sulfide solubility under different conditions, predicted and calculated. And there's a whole thing here in which we are predicting the sulfide capacities. And if those of you who are dealing with slags and sulfur, you may want to look at this whole thing. And this actually goes up now to fairly strong, high concentrations. You can even go all the way up to sulfide systems with it, if they're in fact miscible. Of course, much of this system is hypothetical. For example, you can never have liquid silicon sulfide. So I mean, you can never take silica. The solubility of sulfur in silica is extremely small, so basically the Gibbs energies of even the pure SiS2 is a parameter of the model. I mean, there is no liquid SiS2. It's a parameter of the model related to the silicon-sulfur bond energies. And if the binary one Si2SO is also a parameter of the model. This isn't a parameter of the model. This is a silica calcium system, so the Gibbs energy of this is obtained from the optimization of that binary system. Calcium sulfide, calcium oxide has also been optimized, so this binary. Okay, so certainly these three corners and these two here, these three corners are pure materials which exist. These binary systems exist, so they've been optimized, so the Gibbs energies of these two binary pairs has been determined from optimizing these binary systems, plus all the Z's and everything. These are parameters of the model, as is that, but this is your default average and so on. So you can read the whole thing and see how it's done with the Z's and everything. And this is now what's in the FactSage database under slag A. Slag A is all the oxides plus sulfur for everything. Now we've started out, but we've never got that far, as other anions dissolved in slag, such as sulfate, phosphorus, phosphate, OH minus, F minus, and so on, dissolved in slags. We have not yet applied the two sublattice quasi-chemical model to those systems. We do have an old approximate way of doing it, which has nothing to do with two sublattices, which is called the capacity model, which is referred to in this paper, and you can read about it if you'd like. Inho worked quite a bit on the capacity model for nitrides and things as well, but the capacity model is not this. The capacity model is really only for very dilute solutions of various things in the oxide slags, using an approximation technique which works fairly well, but is limited really only to very dilute solutions. If you do it this way with sulfides, you can go all the way to... Don't make the mistake, however, of using this slag A in a calculation where you've got sulfur and you've also got a fairly high oxygen pressure, because it's wrong. It goes in as sulfate. We do have slag B takes into account sulfate but not sulfide. There's other slags, A, C, D, E, that take into account the different the different anions. And someday we'll start to do this properly. Okay, now I want to talk, alright, so now I'm going to start talking about different kinds of solutions chemically. I'm looking at the models and things. So a bit more chemistry, a bit less of the math, or the math will be stuff you've already seen. So I'm going to start off talking about, well, it's a mixture of a number of things. We'll talk about point defects, which is also non-stoichiometric compounds. All comes down to about the same thing, and we'll basically be applying the compound energy formalism to these solutions, which are always dilute solutions of point defects, or dilute solutions of small deviations from stoichiometry and so on. Let's do a simple example here. This was from the homework problems. This is the homework problem. This is homework 17, number 2. I presume you have an idea of vacancies and metals, but let me read it out. You just have well, then we'll do this together. Calculate the multiplicity as well as the configurational entropy for 1 mole of a metal, which contains 10 to the 17th vacancies distributed statistically on the sites of the crystal lattice. Okay, and because the solution is a very dilute solution, the enthalpy is a linear function of the number of vacancies. So this is a Henryan solution, so the enthalpy is the enthalpy of the pure metal plus the enthalpy of forming a vacancy times the number of vacancies. And raccoon is L as vacancies. Okay, the entropy. Okay. Find an equation for the Gibbs energy as a function of the number of vacancies. Minimize the Gibbs energy to find the number of vacancies at equilibrium. Alright, so let's then look at the answer to this. The answer to this. Alright, so we're going to take the lattice of metal atoms. These are your metal atoms on the lattice, single lattice. And we'll take an Avogadro. Now take a mole of the metal. So we have, and number of atoms is n naught, which is Avogadro's number. Let's say we have 10 to the 17th vacancy. So approximately 1 in a million sites is an empty site. Okay, so we have a metal on these sites, and we have a vacancy on one site, roughly in a million or so. Okay, so this is definitely a dilute solution. The vacancies are randomly distributed, so you have an entropy. Okay, the configuration, so this is your multiplicity, is the number of ways of arranging the n naught atoms and nv vacancies over the total number of sites, which is 10 to the, that's your multiplicity. And the del des configurational is minus r. This is simply a random solution. It's a mixture of vacancies and metal atoms over the sites. So it's a mixture. X is the mole fraction of vacancies. 1 minus x is the mole fraction of metal. Okay, so the entropy is just like mixing A and B. You're mixing vacancies and non-vacancies. So it's x vacancy log x vacancy plus 1 minus x vacancy log x vacancy. And this term is extremely small. So this is approximately just equal to that. First term is the only one that counts. This term is much, much smaller than that. Okay, so as you introduce vacancies, you increase the entropy of the system because the vacancies randomly distribute themselves. Okay, this approximation is because the number of vacancies is very small. So you can actually work it out. If I put in the number of vacancies is 10 to the 17th, and the total number of atoms, sites is Avogadro's number, you end up with the entropy. That's no big deal, but let's see what this means. Now the enthalpy, so that's the entropy, that's the configurational entropy. And the more vacancies you add, the configurational entropy becomes more and more negative. And the configurational entropy, as you add the first vacancy, comes in with an infinite slope. So let me draw the This will be the mole fraction of vacancies going from 0. Okay, and the entropy term, the configurational entropy term for mixing the vacancies is the Gibbs energy then of putting in the vacancies is RT log, this is delta H minus T delta S configurational. So this is your configurational entropy term, which is negative. And so your delta S term, putting in the vacancies, this is your delta S term. As you add the vacancies, this is sort of minus T delta S term. The minus T delta S term comes in like, how's that shape? It comes in with an infinite slope, because it says log of 0 is minus infinity, so it's the same sort of thing. You come in with a slope like that. Okay, so adding vacancies, of course, decreases the Gibbs energy of the system. But adding a vacancy, of course, every time you add a vacancy, you have a positive. Putting in a vacancy is a positive energy. You've got to take an atom out, you're taking off bonds. All right, so the enthalpy, this is the enthalpy of the system, which is the H naught is the enthalpy of the pure metal without any vacancies, plus HV is the energy of forming a vacancy times the mole fraction of vacancies, where HV will be positive. Forming a vacancy is a positive thing. All right. This will be your non-configurational entropy if you want to do that, which is S0 plus SV times XV. This is just a temperature dependence. This is a similar non-configurational entropy around a vacancy. The vibrations change. Okay, so your first term here, the Gibbs energy then of forming the vacancy is the enthalpy of forming the vacancies plus the configurational entropy. The enthalpy, or the enthalpy plus the non-configurational entropy, is a positive line like this. This is a positive at any given temperature. This is T is constant. At any given temperature, the first term here will have a positive slope because you're forming a vacancy is a positive thing. You remove an atom, it takes a positive energy. Okay, so every time you form a vacancy, you're forming a positive energy, and at least a dilute solution is basically linear. Okay, because the vacancies don't see each other, so every vacancy you add gives you exactly the same contribution as the previous. Henry's law certainly applies at 1 part per million. You got Henry's laws applying. Okay, so when you form vacancies, you're forming a negative enthalpy, sorry, a positive enthalpy, which is linear, and the minus T delta S term is positive because you're increasing the entropy of the solution, and this is negative. Minus T delta S is negative, the entropy is positive, but this comes in with an infinite slope. So the sum of the two, if you take the total, the sum of the two then, will have this shape. Always negative at the beginning because of this term coming in with an infinite slope, and this term is not infinite, and then it comes around and starts to go back up. Okay, so this is your Gibbs energy. This is your Gibbs energy curve as a function of composition, looks like that. Goes through a minimum, and that is the equilibrium number of vacancies. Okay. The system will you cannot eliminate the vacancies because the vacancies increase the Gibbs energy of the system up to a certain point, decrease it up to a certain point. Okay, so you might say that a metal at equilibrium has a certain equilibrium number of vacancies in it. It's not unless you're at 0 Kelvin, every metal, pure metal, has an equilibrium number of vacancies. You can't avoid them because they increase the entropy of the system. Okay, and the Gibbs energy, when you look at the Gibbs energy of a metal in the literature from the tables of thermodynamic properties, you're not talking about this value because that you can't measure. You're talking about this value. This is your equilibrium metal here. It's not up here. This is a hypothetical thing. Okay. Now this is usually pretty small at lower temperatures, okay, but this is your equilibrium value. So the idea being that a metal at equilibrium does not have no vacancies. A metal at equilibrium has vacancies. So we take the Gibbs energy here, and what is the minimum? Well, we said dg dxv equal to 0 to find the minimum point. We end up with this equation, and putting this around this way, you end up with this equation here. The equilibrium number of vacancies is equal to the exponent of the energy of forming the vacancies over RT. It's a thermally activated process. It goes up exponentially with the temperature. So at low temperature, the number of vacancies at room temperature is extremely small, but it's going up exponentially. So when you get up to a metal at 1,000, 1,200, 1,300 degrees, you can have a fairly appreciable number of vacancies. 100 parts per million, that sort of thing. Okay, not negligible. And these, of course, affect to some extent the thermodynamic properties slightly, but they certainly affect the transport properties. This definitely affects the diffusion. I mean, you know, the diffusion goes by hopping through vacancies. If you have diffusion in a metal, the metal has no vacancies, you don't get any diffusion. How can an atom move through the metal if there's nothing? It has to force its way through the other atoms. But if you have vacancies, if you have metal atoms in your lattice, and here you have a vacancy, well then this metal atom can hop into the vacancy. In other words, the vacancy's over here. Then this metal atom hops into the vacancy, and now the vacancy's over here. So you say the vacancies are moving this way, but that's equivalent to the metal moving that way. So basically your diffusion coefficient depends upon the concentration of vacancies. And since the concentration of vacancies goes up exponentially with temperature, your diffusion coefficient also goes up what? Exponentially with temperature. That's 1 over T. Okay, so log of your diffusivity varies as 1 over T, as in any thermally activated process. Okay. What do I mean by a thermally activated process? I mean there's a process in which you're creating higher entropy, but to create the higher entropy you have to have a certain amount of energy. You cannot, if you supply to the system an amount of energy equal to 1/2 HV, you don't get a vacancy. You have to apply HV, and then you form the vacancy. Okay, when you do that sort of thing, you have a thermally activated process, then you always get this log X versus 1 over T. So it's an exponential thing with 1 over T. As you increase the T, the number of vacancies goes up exponentially. Since the number of vacancies, since the diffusion coefficient depends on the number of vacancies, the log diffusion coefficient also goes up that way. Okay, if you have, you know, semiconductor theory, you have the valence band and the conduction band with a gap energy in between. And in our semiconductor theory, right, to get an electron actually conducting, you have to promote it up to the conduction band. Once it's in the conduction band, it can move through the thing, but the number of atoms in the conduction, so the conductivity, electrical conductivity depends upon the number of atoms in the conduction band. Okay, so the number of atoms, the concentration of electrons in the conduction band is, well, some sort of a constant times the exponential minus the gap energy over RT. The gap energy is the energy, the electron has to get that amount of energy in order to get up here, then it can move. That's the same thing as here. You have to get that much energy in order to form the vacancy, and then you've got your vacancy. Okay, so that's why if you plot log of electrical conductivity versus 1 over T in a semiconductor, you get the same type of thing, thermally activated process. Vaporization is a thermally activated process. Okay, an atom has to jump off the surface of the liquid. You have the liquid here. Up here you've got the gas. To get into the gas you have to have a certain amount of energy has to be formed to get the thing up into the gas, which is the delta G of vaporization. Okay, and if you plot log vapor pressure versus 1 over T, what do you get? You get a straight line. It's thermally activated. You need a minimum amount of energy to get the thing off the liquid into the gas. And log P is the number of atoms in the gas phase, analogous to the number of vacancies formed here. Okay, so you see that the number of vacancies which you'll have depends on the energy of forming the vacancies. The harder it is to form a vacancy, of course, the fewer vacancies you got, but it also depends extremely strongly upon the temperature. So I actually calculated, this was the energy, 22,500. It was, and I believe if you look at the problem, okay, for gold, actually, you know, you can calculate the energy of forming a vacancy roughly from, you can do even that from first principles calculations, you know, the energy of taking the atom out of the bond, out of the thing. This is the energy of forming a vacancy, is about 22.5 kilocalories per mole of vacancy, and that's the configuration, so it's definitely very positive. That's like 90 kilojoules per mole. And the non-configurational entropy is positive. What fraction of the sites are unoccupied at 800 degrees? So you just go back into the formula here, and I let the enthalpy be 22,500. The enthalpy is 8.4, and at 800 Kelvin you get 5 times 10 to the minus fifth. If you went up to 1,000 Kelvin, you'd start to be at 1 or less than 10 to the minus fifth, so you got more and more. And this is important for the transport properties. It can even, when you get really large, we've done some, when we did the magnet database, the magnesium database for some of these alloys at the higher temperatures, the actual experimental data is such that the actual number of vacancies can actually make a measurable effect on the volume of the system. Okay, so this is just to show you. So a vacancy is a point defect, and you always have in any system the number of point defects will not be 0 unless you're down at 0 Kelvin, and it generally is a exponential function. Now I wanted to show now what may seem like a change of okay, now I'm going to go back to this, I'm jumping around this file number 1, the old chapter here, and we're going to go to page 64. All right, and now we're talking about now applying the compound energy formalism. And we're going to talk about an interstitial solution. Okay, so the sublattice model, we've used the sublattice model to talk about mainly things like molten salts now. Okay, but now we're going to start to apply it to other kinds of solutions, and we're going to talk about an interstitial solution. So consider the face-centered cubic phase of the iron, vanadium, carbon system. So carbon goes into FCC, iron, and vanadium on the interstitial sites. Okay, so you have all the lattice sites are occupied by iron, and the carbon can go into the interstitial sites. You all know that. And what we do is we're going to model this now. So you can model this straight, but we're also modeling it using the compound energy formalism. The idea of the compound energy formula I'm trying to show in a lot of these examples is that the compound energy formalism is not a model. It's a formalism into which many, many different kinds of models can be placed. So the molten salt model can be put into the compound energy formalism. And let's here we have iron, and up here sorry, no. Okay, we're talking about 2 sublattices. The 2 sublattices are the metal sublattice, onto which the iron and vanadium randomly mix, roughly, and we have the interstitial sublattice. In the pure metal, the interstitial sublattice is empty. It contains only vacant sites. And then your carbon goes into some of the vacant sites. So we're really only dealing with a system that's quite dilute in carbon, a few percent at the most. Okay, so we have 2 sublattices here. On one sublattice, the iron and vanadium are randomly mixed, and on the other sublattice, the carbon and the empty sites are randomly mixed. Okay, so most of the sites on the interstitial lattice are empty. Okay, and the carbon is going randomly into those sites. So we're going to use the sublattice model, and we're going to write it this way. Here I'm going to write in this corner. So remember, each corner, the model is as follows. Iron and vanadium are on that sublattice, and on the other sublattice you have carbon and you have vacant lattice sites. Okay, so now in this corner down here, down in this corner you have FeVa, so this is pure iron, in which all these sites are occupied by iron, and the Here the interstitial lattice is vacant. So this is your one end member is iron vacancy. Over here you have vanadium vacancy. Up here you have iron carbon. This is not the compound iron carbide. This is a hypothetical thing in which all the this is a hypothetical compound in which all the interstitial sites are occupied by carbon. And this is another artificial compound. Okay, so using the compound energy formalism, we write it this way. It's every end member has a Gibbs energy. And so this is the mole fraction of iron times the mole fraction of vacancies on their sites, etc., the product of the mole fractions. So that's your G0 term. Then you have your random mixing term. Your random mixing term then is the iron and vanadium mixed randomly on the metal sublattice, and the carbon and the vacancies mixed randomly on the anion sublattice. This was written in 1991. Today these x's would be replaced by small y's. These are site fractions, of course. Okay, so this is your compound energy formalism. We're assuming the same number of, assuming that each mole of lattice has 1 mole of, each mole of metal has 1 mole of sites, which is true in the face-centered cubic lattice, where x iron is 1 minus x vanadium and x carbon is 1 minus x of vacancies, are the site fractions on the two sublattices. This is all explained here then. You could have an excess terms which you could be added for fine-tuning if you want. Okay, so your parameters of your model then really are these. The main parameters of the model are always the G0s, these G excesses. There is a G excess along here, of course, which is obtained by the from the iron vanadium optimization. And you could have a small G excess. These are the G excess terms are the alpha 1, 2, XA, XB. Definitely you would have that for this system. And you could put in, you have experimental data over a small region here up to the limit of solubility and over here, so you might want to put in a small term. But the most important parameters of this system are the G0s. Now the G0s of this, G0 of this is just a G0 of pure iron. The G0 of vanadium is a G0 of pure vanadium. This is not the G0 of FeC, this is the G0 of this hypothetical compound. And as G0 here, these two here, things here then are parameters of your model. And if you solve this whole thing as you allow G0 of FeC to become more and more positive, this becomes more and more positive, and your solubility here is going to be decreased. Okay. The more positive, so you could, if you know the solubility of carbon in iron, okay, then you can get the value of G0 FeC that will give you the known solubility. If you know the solubility of carbon in vanadium, you can get the value of G0 Vc that gives you the known solubility here. And then you're using this model. Now you've got an interstitial model, but you fitted it into the entire, okay, is that clear? Because of the entropy terms here, you'll always get some solubility of carbon as the Gibbs energy goes down, but then if this G0 here becomes more and more positive, you'll eventually, the Gibbs energy will come up and you'll reach a solubility limit of some sort, so you can calibrate the model. Okay, so these are your model parameters, which will fit the whole thing in between as well. Okay, the idea here then is that you don't have to write a separate algorithm, you don't have to write a separate model number to treat interstitial solutions. The whole interstitial solution thing can be fitted into the same compound energy formalism, model 15, and we use the same equations as we use for molten salts, for example, with 2 sublattices. So you can use it for any sublattices. It's called the compound energy formalism because you're treating FeC and Vc here, the Gibbs energy, you're treating these as, quote, compounds. They're not really compounds. The G0 of FeC is not the Gibbs energy of a compound. What you've really got is G0 of FeC minus G0 of Fe vacancy, which is just Gibbs naught. That is your model parameter. The Gibbs energy of FeC minus the Gibbs energy of Fe, pure Fe with the vacancies, is basically the Gibbs energy of putting a carbon into the vacant site. This is the Gibbs energy. This is the Gibbs energy of a hypothetical compound where all the vacant sites are occupied by carbon. This is the Gibbs energy of iron, where there are no interstitial sites occupied by carbon. The difference is the molar energy for putting carbon into the interstitial sites. It is really only meant to apply over the dilute solution. Okay, so it's sort of like a Henry activity coefficient, if you like. This is simply the energy of putting carbon into the vacancy, into the lattice here. So this is your model parameter. This I call the formalism parameter. This minus this is your model parameter. The real model is, what is the model parameter? What is the physical, a parameter that has a physical meaning? The parameter that has a physical meaning is this difference. It's the energy, which is the energy of putting a carbon into an interstitial site. It's that difference. It's only meant to apply over this region. Okay. That's your model parameter. This G0 FEC is your formalism parameter. That's what you put in when you're doing your entry into fact stage. You put in these G0s. Okay, but the G0 of FEC is not really a model parameter. This is your model parameter. This is what has physical meaning. Okay. So your formalism parameters are your n-member Gibbs energies. Your model parameters are the actual thing that has a physical meaning. If you're trying to model this, you're trying to model the energy of forming an interstitial, putting a carbon into an interstitial site, and that's what the difference is. Okay, the idea though is what makes it cool is that you can then use the same formalism, the same model as you're using for as we use for real solutions. So this FEC and VC are not real compounds; they're pseudo compounds. Okay, so the difference between a model parameter and a formalism parameters. Now, in these particular corners, the Gibbs energy of pure iron is a model parameter, and it's also a formalism parameter. Well, it's not even a model parameter. I'll get this model parameter. But I'll show you what I mean. This distinction becomes really important, and it's often lost. Also, just to get ahead of myself, but I've said this before, the tendency is people forget the difference between a model and a formalism parameter. And if they don't have information for a formalism parameter, they'll set the formalism parameter to be 0. You don't do that. You set your model parameters to be 0, not your formalism parameters. Okay, let's talk about now non-stoichiometric compounds. So this is page 65 in the file number 1. Non-stoichiometric compounds. And we can treat these generally by a simple sublattice compound energy formalism. And we're going to talk now, I'll draw this over here. So let's take a compound. Actually, I already did this last week for the magnesium yttrium thing, but let's do a simpler one here. Let's say we have a compound AB. This is your compound AB in your phase diagram. So this is a region in which your compound AB is stable, and it has non-stoichiometry. Generally, as you go down to the lower temperatures, it comes down to being AB, but at higher temperatures, you can have a deviation from the stoichiometry AB. All right, so now we want to treat this. We want to treat the non-stoichiometry of the compound using a using formalism here some way. Okay, how do you get a deviation from, if you have a deviation from random mixing, if you get a deviation from the AB stoichiometry, how do you get this? And there are many different ways it can be done. So let's take the stoichiometric compound AB. So there you've got two sublattices, AB, AB, B, A, B, A, AB, AB. So that's your stoichiometric compound. Now, if you're getting a deviation towards, say, that's 50-50 here, if you're getting a little excess B or excess A, there's different ways that this can happen. This is happening by point defects. One type of point defect would be to have a B occupy an A site. So rather than have an A here, we have a B occupying an A site. That's called a substitutional defect. And that then moves you over towards a solution that's richer in B. Okay, or you can have an A occupying a B site. And that is another type of point of substitutional defect. Okay, so on one side you have excess B substituting on normal sites which are normally occupied by A, and so on, and that's how you can get the deviation from stoichiometry. Okay, so let's consider the solution in which the majority defects are A atoms on B sites and B atoms on A sites. Okay, so we can write it as A. Here's your A sites, your A sublattice, and this is your B sublattice. So you can have A's and B's on the A sublattice, and you can have A's and B's on the B sublattice. Normally, the normal situation is to have little x to be 0. So in other words, these sites are occupied by A, and to have little y equal to 0, these sites are occupied by B. Alright, so we can draw this thing this way here. Let's put AB. Okay, so then here we're adding y. No. Yeah. Y, and this would be x. Okay, so this is your stoichiometric compound AB with all the A sites occupied by A and all the B sites occupied by B. And now we're starting to replace some of the B's by A's. So over here we have your hypothetical compound AA with all the B sites occupied by A's. Okay, up here we have B, and over here we have BA. Now the only region that you're really dealing with is this corner down here. Okay, because you're only going a small ways. You're only going a small ways from stoichiometry. You're adding a few substitutional defects either way before you run into your solubility limits. Right, but so this compound here, sort of similar to the interstitial thing I just gave, this is a hypothetical compound. It's not pure A. This is not pure A. This is a compound in which it's the structure of AB in which it's 100, all the B's have been replaced by A. It's a hypothetical thing. You can't go that far. But it's 100% defects. This is 100% defects. This is 100% defect. This is not the same as AB at all. This is much more positive Gibbs energy than AB. This is an AB with all defects here and all defects here. So these are hypothetical compounds. Okay. But what we have is the actual solution then is given by the Gibbs energy is you're mixing 1 minus x, 1 minus y, Gibbs energy of AB, plus 1 minus xy times the Gibbs energy of AA, plus x1 minus AA, plus xy times G naught BA. And then you have the A's and B's are mixing randomly on the A lattice, and the A's and B's are mixing randomly on the B lattice. Generally for these things you're dealing with small regions. You can forget the excess terms, you can forget the big lambda. The most important thing are these parameters here. So now I think you can see what's going to happen as you G naught AA, as G naught AA becomes more and more positive, the energy, this is basically your model parameter is the difference between G naught AA and G naught AB. It's the energy of putting a vacancy into the lattice. As you make that model parameter more and more positive, you're going to decrease the solubility here. Because the difference between this and this influences the solubility here. It's the energy of putting in a vacancy, putting a substitutional defect into that lattice. Okay, let's work this out just to show you what would happen. Now this can all be done by fact stage, but let's just see let's look at the actual mathematics. G naught AB is the molar Gibbs energy of hypothetical defect-free stoichiometric AB. Now what do I mean by that? Why isn't this the Gibbs energy of real AB? Well, because even at the stoichiometric, even when you've got at 50%, even when you've got a compound at 50-50, say here you've got a compound containing the same amount of A as B, you're still going to have defects. The number of B defects will equal the number of A defects. will be equal, but they're not zero. It's exactly the same thing as I showed the number of vacancies in a pure metal. Number of vacancies in a pure metal at equilibrium is not zero. It's determined by what minimizes the Gibbs energy. Since forming these substitutional defects increases the entropy, even though their energy of forming is even though the enthalpy of forming them is positive, they have an entropy. So you always get. So this G naught of AB is not exactly the Gibbs energy of real AB at 50%. It's the Gibbs energy of a hypothetical defect-free AB. Now the defect concentrations at equilibrium are those that minimize G. So we set dg dx equals dg dy equals 0. At a delta, delta is the deviation from stoichiometry. Okay, delta is x minus y. Delta is 0 at 50%. Delta is positive on one side, negative on the other. Okay. The compound is actually, we can write, this is the way we often do it. We write the compound as A1 minus delta, B1 plus delta. Okay, if delta is 0, you're at 50-50. If delta is positive or negative, you're on one side or the other. Sort of the standard notation. Okay, and if you do this, you take this equation and set dx, dg dx, dg dy, you end up with an equilibrium constant. This is the number of defects. X's and Y's are the number of defects. So xy over 1 minus xy is my is, if you work it all out, you get this. And you get delta G1 plus delta G2 over RT, where effectively this is what Faxage, equilib doesn't write this equilibrium constant out, it just minimizes the total Gibbs energy, but this is what's happening. I'm trying to show you what this means mathematically, where if you work this whole thing out, delta G1 is G naught AA minus G naught AB. Okay, so this delta G1 is G naught of the AA minus the G naught of AB. And as I said, that's the energy of putting a mole of vacancies into here, into the dilute solution. Okay, and delta G2 is the same thing for up here, G naught BB minus G naught BB. They are the Gibbs energies of forming the majority defects. Now these are called the majority defects. I'll say later what that means, but in this case the majority defect on the right side is a substitutional defect of B on an A site. The majority defect on the left side is a substitutional defect of B on the A sites. And this is really wrong, and we should not be doing this. So I'm going to change it. This was written 20 years ago, and I really was kind of dumb. And I said, and where G naught BA has been set equal to G naught AB. You really shouldn't do that. It doesn't make an awful lot of difference. Well, AB is the same as B. No, it isn't. BA is a totally hypothetical thing in which you have only defects on both sides. Okay, a better way to do it. And this in fact, you almost always will see this in the literature, but this isn't really the right way to do it. Okay, so I'm making the same mistake as before. So what you really should do is you should set G naught. Pick up the wrong one. Throw this in. So the G naught of BA is really the Gibbs energy of forming both kinds of defects. So what you really should do to do a proper value, what is your default value of G naught BA? You really should set G naught of BA to be equal to G naught of AA plus G naught of BB, the energy of forming both defects, minus the Gibbs energy of the AB. That would be a more logical way to do it. That makes more sense. That makes more sense, and actually if you do that, you look back to this equation here, so don't cross this out. G naught BA has been set equal to G naught AB. What you should do is you set G naught BA equal to energy of forming both kinds of defects minus G naught AB. Makes much more sense. When you do that, by the way, then this equation here actually becomes simpler. This funny looking term 1 minus x minus y drops out. and this is even simpler. It's just xy over 1 minus x 1 minus y, which is really the equilibrium constant for forming the defects, equals exponent of minus delta G1 plus delta G2 over RT. That's 1 minus x minus y drops there. Okay, so you can see that then as the energy of forming the defects, the delta G1 and delta G2 become more and more positive. The number of defects here decreases. Okay, xy is the number of defects. So if delta G1 and delta G2 are more and more positive, the number of defects becomes smaller and smaller. And on the phase diagram, the range of stoichiometry will shrink. Okay, now what you'll also see is the delta G1 and the delta G2 control the two different sides. If delta G1 is large and delta G2 is small, then you're going to get a lot of solubility on one side but not on the other side. If this model parameter delta G1 is very positive, you'll get, as the delta G1, which is this difference, becomes more and more positive, you shrink the solubility over here. Okay, and delta G2 affects the solubility over here. So if delta G1 is very, okay, so that affects how far you go on each side. If you have a system in which the sometimes you'll see systems like this in which the solubility only opens up on one side. So in other words, this comes down on one side here, it's almost always stoichiometric AB. It hardly deviates from 50-50, but it opens up wider on this side. That then tells you that the energy of forming this kind of substitutional defect is much less than the energy of this kind of substitutional defect. So to get this, to have a system that's almost stoichiometric at 50-50 but opens up to A, then what we have to do is we have to make G0 of B, delta G2 quite positive so that this decreases, and make this less positive, delta G2 that one less positive, so you get more solubility on that side. So each of these two parameters independently determine the opening up on the two sides. Okay, the two parameters together, however, if you're at 50-50, then x equals y. If you're at exactly 50% AB, then x equals y. Okay, the number, obviously the number of defects must be the same, but they're not zero. And then the delta G, you solve this equation, you can find the number of defects at the 50-50 composition. Okay, and that then permits you then when you go back into the Gibbs energy equation, then, okay, you will get the Gibbs energy of the system at 50-50, which will not be exactly G0 AB. This will be your Gibbs energy of your real AB, which contains the defects, not the Gibbs energy of the hypothetical AB. If the delta G1 and delta G2 are extremely positive, then x and y are 0, and then if you put x and y and 0 in here, you end up with G is equal to G0 AB, but otherwise it's... Okay, so when you're doing your optimizations, if you have a large amount of non-stoichiometry, remember, and you're using this model, remember that this G0 AB is taking into account, this G0 AB is a hypothetical thing, and it's not the actual Gibbs energy of the real AB. The real AB at 50-50 will have a slightly more negative Gibbs energy than this hypothetical affair here. Now once again, now we're at the difference, the model parameters and the formalism parameters. Delta G1 and delta G2, this delta G1 and delta G2 are your model parameters. These things have physical meaning. They're the energy of forming the vacancy, the substitutional defects. GAA and GBB and GBA are formalism parameters. They don't have physical significance. They have physical significance because they're differences of... Okay, but now once again, now we have a model for a system with substitutional defects. But rather than having to write a separate algorithm, a separate model, we can fit the whole thing into the same model number. We can use the same input for fact stage, the same algorithm, and just by defining your G0s and things properly, you've got now your substitutional defect model. Okay, so that's your compound energy formalism. These things are not compounds, okay, but they're treated as if they were compounds using the compound energy formalism. Now I gave you another example back here, number 23. We went through it the other day. It was exactly the same thing. And you probably will notice that it was exactly the same thing. And now I talked about magnesium fluoride. This was your Lattice phase, your Mg2Y, which is a non-stoichiometric compound. Okay, and it's treated exactly the same way. The only difference now is that the number of sublattice sites is different on the two sublattices. So here we have I already did this, but you're treating this as mg2y. That's your minimum now is not, it's not AB, it's A2B. Okay. It's A2B here at mg2y. Okay, so you're using your compound energy formalism, but this is mg2y. Over here you have y2y. Over here you have, well, how do I do y2y, whatever. What was the other way around, just to do it the same thing, mg2mg. Up here you have y2y, and up here you have y2mg. You do exactly the same thing, you're just taking into account the fact that the stoichiometry is different. Okay, the meaning is exactly the same. Your model parameters are g naught of this minus g naught of this, and g naught of this minus g naught of this. The g naught of this is given by, it's just two sites on this lattice and one site on the other lattice. And the equations are right there. Okay, and it's exactly the same thing, and you can see that it's fitted. And in this particular case, you can see when we did the g. The one model parameter is very positive because the solubility is almost entirely on the left-hand side. Okay. So in other words, we made the y2y here very positive, such that the solubility limits are sort of like this. Okay, so again, the idea is to the difference between the model parameters and the maybe I'm going. If this confuses you, if it does, this was AB. Go back to the example I had over there. AA, BB, BA. So I said G naught of AA minus G naught AB is the energy you're putting defects in. So G naught AA is a formalism parameter, and it is not equal to twice the energy of pure A. You don't take pure A here, you don't, just like the Mg2. Mg2Mg is not the same thing as pure magnesium. Okay, this is just a hypothetical compound. There are cases, occasionally, when it isn't a hypothetical compound, when it has exactly the same structure as the compound. In that case, you can imagine your phase diagram. There you might have your compound AB. Let me drop that. I'll do that later with ordered solutions. I was going to say that if the Lattice phase was exactly the same structure as hexagonal compact magnesium, then it would be an ordered phase. It would be an ordered form of that structure, and therefore you really should take this, because you have a miscibility gap, but at higher temperatures you could actually have. I'll do that when I talk about order. Okay. In most cases, this is what I've said here is correct. Okay. Unlike, as I said here, when you have, if you have quite a broad range of stoichiometry here, a few percent, then at 50%, I said at 50% that you don't have the pure, the 50% compound is not defect free. And now, of course, unlike the vacancies in the metal, you're not talking about 1 part in 100,000. You could be talking about like a lot, percentages. So several percent could be defects. In that case, of course, the G naught of this hypothetical AB is nowhere near the G naught of real AB. It can be quite different. Okay, these two kinds of defects are called the majority defects. So there's another way that you can. There's other ways that you can have deviation from stoichiometry. I'm going to have to excuse myself for a minute. It's still a bit cold here.
what A is side again, it will be replaced by what B side will be replaced by and then take input it is some possibility also we have the x and y can really activate इसे तुम्हारा
Just finish this last part. Let's consider, it continues on here. Okay, so that was, in this case, you're explaining your non-stoichiometric compound by defects, which are substitution. These are substitutional defects. Okay, I'm consider another model, which the majority defects are vacancies on the B sublattice and B atoms on interstitial sites. So, let's go back to the stoichiometric compound, and then what I said, you have vacancies on the B sublattice. So in this particular case, the way you get excess A is by simply removing B and forming a vacancy rather than having a substitutional, and the way you get excess B, B atoms in interstitial sites. So the way you would get excess B would be to have a B atom go into an interstitial site. Okay, so now you have two other kinds of different kinds of defects in which to deviate from stoichiometry towards this side, you're putting vacancies on the B lattice, and to deviate going on this side, you're putting B atoms into the interstitials. Okay, so now your model is going to be the following. The pure A would be A, B, and we're going to have to introduce an interstitial lattice in which we'll have vacancies on the interstitial lattice. So this is your stoichiometric material. A on the A sites, B on the B sites, and vacancies on the interstitial lattice. Over here we'll have A, B, and B on the interstitial lattice. I'm going to put the interstitial lattice in brackets just to separate it. Okay, so here you have A, B vacancy. Now we're putting B's into the interstitial lattice. So over here we have a hypothetical compound which has A's and B's, and then it also has B's on the interstitial lattice. Up here we're going to have the other way, so we're going to have A, vacancy. So the vacancies on the B site. So up here we have A, vacancy, and over here we will have A, vacancy, B. Okay, so those are our N numbers. Okay, so the end members can be written this way: A, B, vacancy, vacancy, B. These are your A sites, these are your B sites, these are the interstitial sites. Okay, that's your sublattice model. Now we really have 3 sublattices, but the first sublattice we can forget because it's always occupied by A. Right, so it's really a 2 sublattice model. Okay, so we forget the A sublattice, it's the same everywhere. So we're really dealing with a 2 sublattice model, in which we're mixing B and vacancies on these sites, and we're mixing vacancies and interstitials on that site. So here we go. We have A on the A sites, B and vacancies on the B sites, and B and vacancies on the interstitial sites where I indicate the interstitial sites. The okay. Stoichiometric defect-free AB is represented by AB vacancy. All this mass balance here, I don't know, this doesn't really, I was trying to put this into your standard notation, that if you have the, if we're still treating this material as A, if we want to write it as A1 minus delta, B1 plus delta, then if you do a little mass balances, you find, okay, this would be, sorry. This, I better do that because the red doesn't show up. This is a little X along here, and this is a little Y along here. Okay. Okay, X and Y on this direction. So forget the 1 minus delta. I just put the 1 minus delta. It doesn't matter much. That was just trying to make the masses balance. It's still in the sublattice formalism. It's in the compound energy formalism. It's this, the Gibbs energies of your, same thing as before, the Gibbs energies of your end members, where the Gibbs energy of AB vacancy is the Gibbs energy of defect-free stoichiometric AB. This is, and it's the same thing. Your model parameters are just like before. Your model parameters are delta G1 is the Gibbs energy of your ABB minus your Gibbs energy of AB vacancies. In other words, that is the difference between this and this, which is the energy of forming a B interstitial. And the same thing on the other side, your delta G2 is the Gibbs energy of A vacancy minus the Gibbs energy of AB vacancy, and that's this minus this, and it's the Gibbs energy of forming a vacancy on the B side. So your model parameters, before in the substitutional model, the model parameters was the energy of forming a substitutional defect. Now it's the energy of forming an interstitial defect here, or the energy of forming a vacancy defect here. Okay, your defects are B lattice vacancies, and B's on interstitials are your. Okay, so your model parameters are still this minus this and this minus this, which are the energy of forming the energies of forming the majority defects. This thing up here should be the same thing. The Gibbs energy of this thing should be this plus this minus this, just as we did before. Okay, and you can see this, it's almost exactly the same model. Right? It's going to be almost exactly the same equation. The only slight difference was that if you do the mass balance, there's a little bit of difference here, 1 minus delta, because you're changing. As you introduce B, you're actually changing the total number of moles of material, whereas before you didn't. But this is trivial. The point is, it's almost exactly the same equation. You get almost exactly the same. If you minimize it, so you take the same equation here. You take the compound energy formalism, you set dg dx equals dg dy equals 0 to get the equilibrium values, as we did before, and you end up with an equilibrium constant that's almost exactly like this. In fact, you'll have xy over 1 minus x1 minus y, which is the same, the concentration of the defects, delta G1, delta G2, and it just might be a slightly different small, almost one term in between. And once again, the delta G1 and the delta G2 determine how far you are on one side or the other. Okay, and it looks almost exactly the same. And so that's your other defect model. Now these are called the majority defect. So, and once again, pure AB, pure stoichiometric AB will contain an equilibrium number of vacancies and an equilibrium number of interstitial Bs, which at 50-50 will be equal to each other, but they won't be zero. The concentration of vacancies will be the same as the concentration of interstitials, so that you're at 50-50, but their concentrations are by no means zero, and depend on the values of delta G1 and delta G2. These are called the majority defects. So on one side, say on this side now, on the B-rich side, you have mainly this kind of defect. Very rapidly too, by the way. If you move over, as you start at 50-50, then the amounts of vacancies in B are obviously equal. As you go further over this way in the stoichiometric range, you increase the number of interstitials, the number of vacancies rapidly decreases. Okay. Doesn't go to zero immediately, of course, but it rapidly decreases. Or if you go on the other side, the number of vacancies increases and the number of B's rapidly decrease. So these are called the majority defects. The majority defects in B-rich solution are vacancies, interstitial B's. The majority defects on the left side are B-lattice vacancies. Whereas in the previous example, the majority defects were substitutional A and substitutional B. Now, you say, well, why can't we have a system where we have different defects? In other words, we can have, on this side, we can have interstitial B's, but we can also have B on the A side. So you have two kinds of defects as you go over here. And you can. In fact, you always will. But the thing is, the energy of forming one kind, the energy of forming one kind of defect, if it differs by a couple of kilojoules from the energy of forming the other kind of defect, and you do the mathematics, you'll find that this minority defect is really trivial, is really minor compared to the majority defect. You don't, unless you happen to have, by sheer chance, you had the energy of forming a B interstitial was almost exactly the same as the energy of putting a B substitutionally on an A site. In which case, of course, the concentrations of the two defects would be the same. But this is hardly ever the case. You always have a significant difference. One kind of defect is always much more stable than the other kind of defect, so you never have to worry about more than one kind of defect, really, on either side. But it can be the defect on one side and the defect on the other side can be quite different. You can have a substitutional defect on this side, an interstitial on this side, or those are your two majority defects. Now, when I said that these equations, independent of how you decide on the majority defect, the equations are quite similar. And this shows then that thermodynamically, and I've seen this say that, we took a defect model, I've seen this in papers, we take a defect model to we're optimizing a system, so we have a lot of experimental data. You have the phase boundaries and things. And we supposed a defect model in which we had vacancies on one side and interstitial B's on the other side, and it fitted the data perfectly. Therefore, that proves that these are the majority defects. Well, no, because if you put a substitutional defect, you get almost exactly as good a fit. Okay, because it's almost exactly the same equation, as you can see from looking at this. Okay, so just because your defect model fits doesn't mean really anything to these non-stoichiometric compounds. Any model, you could fit the same system. That magnesium yttrium I showed you, we know that that's the way it is because we have other evidence from the lattice parameters and the X-ray diffraction and so on, that that's the model. But if we'd chosen a different model, so in that case it was substitutional, but if we chose a different model, the vacancies and interstitials, we would have got just as good a fit to the phase diagram. Okay, so that doesn't tell you an awful lot. Just because it fits your defect model doesn't mean your defect model is right. On the other hand, it means if you don't know the defect model, you can still get a damn good fit to your phase diagram. Okay, so it works both ways. The other question then is, does it really matter then? And it can, if you want to go into, say, ternary systems, you're going to put a third component into it and this kind of stuff. It can make a difference, but sometimes it would, sometimes it wouldn't. Okay, but anyway, just be careful that just because a model fits doesn't mean that model is definitely right. Like, well, going back to the idea in the associate model versus the quasi-chemical model. The associate model fits nicely because this is basically the equations in the binary look the same, but when you go into the ternary, the equations don't look the same. The same thing can kind of happen here. Okay, so you can get a nice fit to the binary with any defect model, but it won't necessarily be the case in the ternary system. Also, well, let me give you an example. Let's supposing that this word, that you use this model, and then we're going to go into the ternary system and add C. Now let's say C is a bigger atom than B. In that case, if C is a big atom, it ain't going to go in interstitially. So your guess, your first guess, if you had no data, your first guess would be that C was not soluble in this compound. On the other hand, if the B was going substitutionally with A, then it's easier to substitute here. In that case, C could replace B. In this case, C can't. So how the non-stoichiometry goes, it's a little more complicated, but I mean the model, again, I mean an interstitial model is only good if you have smaller atoms. But once again, we have a different model, vacancies, interstitials. It very easily fits into the compound energy formalism without having to come up with a different model every time. Okay, but again, the important thing is separate your model parameters, which are the things that have physical meaning, from your formalism parameters, which have no physical meaning. If you don't have any data, if you had no data on the system, but you wanted to make some sort of an estimate, okay, this is what you should be estimating, the energy of forming a vacancy, not the Gibbs energy of this thing, which is a hypothetical affair. You should be like estimating the Gibbs energy of that. That's your model parameter. This is not a model parameter, it's a formalism parameter.
Sorry, I have a small question concerning thermodynamic measurements. Since if a person wants to measure some thermodynamics properties of the AB compound, and you've just shown us that the actual composition that they're going to get when they're going to synthesize the compound is going to be somewhere within this, yeah, it's going to be exactly at the corner.
Here.
Yeah, how much is it going to affect their measurement in like the modern compound? If you would like to do on.
Well, some thermodynamic data is going to give you more information than others. You're trying to model the system. Measure. Okay, if you measure the solubility limit here, in other words, measure the phase diagram, you know how far that's gone over.
Yeah.
That permits you to get a value of G naught. That's the easiest way to do it.
Okay.
Then, if you measured the activity coefficient of A as you moved across, all you'd find would be a straight line. It's basically like a Henrian solution. So it's not giving you any extra information, really. You could measure the G naught of B and see when it was equal to activity of pure B, and then say, well, now I've measured the activity coefficient, so when it becomes 1, now or when the activity becomes 1, it's in equilibrium with B, but it would be an awful lot easier just to measure the solubility limit. So it isn't giving you a lot of information. Okay, there's other things that you can measure. Okay, so you will see people that measure activities across the system. And then when you reach the phase boundary, the activity goes up and then it moves across again. And you say, well, that's a very useful measure. But it's a useful measure not because of the absolute value of the activity, but because it showed you where the phase boundaries were. Okay? So,
for example,
phase diagram is really, I mean, if you're looking at something that's really useful, the phase diagram's got an awful lot of information in it. And it has the advantage of usually being more accurately, easier to measure accurately than to measure thermodynamic properties. Measuring enthalpies are really important. The enthalpy of formation of the compounds are very important. If you have the enthalpy of the compound at 298, that tells you an awful lot.
Yeah.
The enthalpy of mixing of liquids is also a very important parameter.
But that's the thing, if you measure the enthalpy of formation of that compound, like which composition, like at which composition is your AB actually?
Well, you usually measure the enthalpy at room temperature, and at room temperature, again, because this thing, remember, it's another thermally activated affair. You see, XY is a product of the concentrations of the majority defects. And as the temperature is very low, this XY product approaches 0. And that's why, if you see a phase diagram in which these phase boundaries come down vertically, it can't possibly be right, and they all come down. At a room temperature, I mean, everything really narrows right down. So you measure it at the stoichiometric composition at lower temperatures. Or you can measure it at higher temperatures, but we'll measure it at 50-50 if you possibly, at the actual stoichiometric composition if you possibly can. I might point out, I think I pointed this out before, but if you have a compound, you can have a compound that can narrow down to 50% exactly, but let's say is much wider on one side than the other, so that when you go up to high temperature, the actual maximum, the congruent melting point, can be significantly shifted to one side. That doesn't mean the compound isn't 50-50, it means that the defects on one side are much easier to put in than they are on the other side. But yeah, measured at 50%, but the enthalpies at 298 are a very big thing, because then if you have, if you have the enthalpy at 298, the melting point basically gives you the Gibbs energy, equal to the Gibbs energy of the liquid, so you can work back to get the entropy. Enthalpies give you a lot of information. And they're also not that hard to measure. You usually find them in the literature. In the liquid state, the phase diagram gives you the Gibbs energy, but it doesn't give you the H and the S. So if you can get enthalpy of mixing values in the liquid, that makes life a lot nicer. Okay, one final comment. If this thing is rather small, if the stoichiometric range is rather small, which it is in many cases, then the denominator here is approximately equal to 1. And that shows that at a given temperature, the product of x to y is constant. Right? X, y is constant as you move across. This gives you also generally a really fairly good approximation too. If you can somehow measure, if you can measure the concentration of vacancies, then the concentration of vacancies times the concentration of the other majority defect will always be constant. Which is useful when you're talking about looking at transport properties. I'll talk about that a bit later. Okay, that's kind of a good place to stop. Okay, so there's nothing next Tuesday. So we'll meet again Thursday. Right? Thursday. However, I now feel justified then, since we're missing that, and giving you a few more things for homework. So we can look up. Where do I put them? They all seem to be going. That one's gone. This one's not good. There's a third one. 17, 11, and 6. People at home can't read red, it doesn't matter, they're not going to do the homework anyway. 2003, examen final, numbers 1 and 3. Exam year 2005, control number 2, number 4. 2006, control number 2, number 5. Those are all in, these are all over the place on the server, but they're all in file number 30 if you scroll down. 2008, number 2. That's in file number 46, and 2009, number 2, and that's in file number 47. Well, that should do it. We'll do for Thursday. Okay, we can turn this off now, then we'll talk about it. Oh, they're up here now.